Welcome back, Chemistry 30. So this is continuing on with the 1.2 electron configurations. This is the part 2, and we just ended off by referring to Hund's rule, which states that for degenerate orbitals, so if I'm placing electrons in, let's say, the 2p region, the 2p's are all the same energy level. That is referred to as being degenerate orbitals. We have to put one in each before we begin buddying up. Let's take a look as to reasonings as to why. So the lowest energy is attained when the number of electrons having the same spin is maximized. This means that electrons occupy orbitals singly to the maximum extent possible, and that these single electrons in a given subshell all have the same spin quantum number. So they could be spin, so we could have them as upward arrows or downward. Electrons arranged this way are said to have parallel spins. For a carbon atom to achieve its lowest energy, therefore the two 2p electrons must have the same spin. For this to happen, the electrons must be in different 2p orbitals, as shown in the table. Thus, a carbon atom in its ground state has 2 unpaired electrons in that region. Similarly, nitrogen, of course, nitrogen has one more added, and if we take a look here, yes, 1, 2, 3, so 1 in each of the 2p orbitals. This is the only way that all 3 electrons have the same spin. For oxygen and fluorine, we place 4 and 5 electrons, and then we begin to pair them up, of course. So yes, with oxygen, yes, or I guess I don't have it here, but neon, we double them up, and then we get the maximum amount. Now here we go. Hund's rule is based on the fact that electrons like to repel each other. By occupying different orbitals, the electrons remain as far apart from each other as possible, thus minimizing the repulsion that they would feel if they were closer together. So let's take a look at this example. So on the next page here we have this. Draw the orbital diagram for the electron configuration of oxygen, which is atomic number of 8. How many unpaired electrons are there, and how many unpaired electrons does an oxygen atom possess? So 8. So what we could do here is, okay, so we'll look here. Here's our orbital. We're going to fill up the 1s region, then the 2s, then we'll look at the 2p. That's likely as far as we need to go. So this sheet is nice because it shows you the order of filling. 1s, 2s, then 2p's. So I'm just going to draw that, and I'm going to draw that sideways just to minimize space here. So there's the 1s orbital, the 2s orbital, and then the 3 2p's. I'll just draw them I guess I could attach them here, but I'll just draw them like that. So 8 electrons given by atomic number 8. So first of all, we put an electron in the 1s level, and then we can immediately buddy it up with another one of opposite spin. Same thing here, and same thing here. Now, so I've used up 4, I need to go 4 more. So in the degenerate set here, an electron goes in each one, first of all. So 1, 2, 3, 4, 5, 6, 7, and then, yes, the 8th one goes back here. Now, if we're writing the electron configuration, a summary of what we have here, in the 1s region, we have 2. In the 2s region, we have 2. And in the 2p region, we have 1, 2, 3, 4. So 1s2, 2s2, 2p4. And of course our unpaired electrons are right there. Easy, so that's how we do that. And let's see, oxygen, if I was to go 2 more, then I would get to the noble gases have 2p regions filled up, which leads us to this, condensed electron configurations. The filling of the 2p subshell is complete at neon. So hey, what we could do over here is, right, okay, if I was to complete the 2p region, that would fill up neon. Because if you look at the periodic table, 2, 4, 6, 8, 10. Neon has an atomic number of 10. So we would have that completely full. It would have its octet. The next element, sodium, marks the beginning of a new row of the periodic table. So yes, from neon, sodium with its 11 electrons, the next one would go here in the 3s region. And so yeah, we could do is we could have a shorthand way of represent that. So the electron configuration of neon plus the one electron in the 3s1 region would be the condensed electron configuration for sodium. So the symbol Ne represents the electron configuration of the 10 electrons that are used for neon. Running the configuration like this, neon in square brackets and 3s1, focuses the attention to this part, the outer electrons that sodium has, which, as we'll see in the next unit, is responsible for how it behaves. We can generalize what we have just done for the electron configuration of sodium in writing the condensed electron configuration of an element. We take a look at the nearest noble gas that was just below it on the periodic table. So, for example, lithium, which is atomic number 3, well, helium I know has atomic number of 2, so I could talk about that and then put the additional one in there. So if you have a periodic table in front of you, you can easily see that. Let's see here. I think I have, I do have one here somewhere. Mine's kind of funky looking though. Here we go. So yeah, we'll get to this here, but yeah, I guess it doesn't have it. So helium is right here. So helium, and then lithium here is at 2s1. So yeah, we could do that. So in fact, we could put, for your little sheet here, we could look at all the noble gases that fall in that specific region. If I was to fill up the 3p, that would be argon. Was here? No, argon. And if I look at the 4p region, that would fill up krypton. And of course, if you notice here, there's overlapping. The 4s region is actually lower than the 3d, so that's kind of interesting how it overlaps like that. But for now, hey, let's put these noble gases here so that you know that if I fill up the p regions, that gets me to the noble gas. So if we look at the next page, we refer to the electrons represented by the bracketed symbol as the noble gas core. So the noble gas that immediately precedes it. More usually these are called core electrons. And the electrons given after the noble gas core are called outer shell electrons. And another name that we'll use, and this will come into play next unit, valence electrons, outer electrons. For the elements with atomic numbers 30 or less, all of the outer shell electrons are valence electrons. By comparing the condensed electron configurations of lithium and sodium, we can appreciate why these two elements are so chemically similar. They have the same type of electron configuration in the outermost shell. Indeed, all the members of the 1A group have this happening. So yes, if we look at, let's grab that periodic table again. So if I look over here at the noble gases, so whatever configuration they have, and if I add the next electron, that gets me to the 1A. So if you take a look at the condensed configurations for some of these, lithium, helium, and 2s1. Sodium is neon and 3s1. Potassium is, well, argon and 4s1. Notice they're all 4s1s. Oh, look at that. And they just happen to be in group 1A. So that's interesting how that happens, and that's why they're very similar. If you look at the transition metals, the noble gas element argon marks the end of a row started by sodium. The element following argon on the periodic table is potassium, right there. In all of its chemical properties, potassium is clearly a member of the alkali metal group. It's very reactive with water, for example. The experimental facts about the properties of potassium leave no doubt that the outermost electron is in the s orbital. But this means that the electron with the highest energy has not gone into a 3d orbital, which we might expect to do. Because the 4s, yes, we mentioned that the 4s orbital is actually lower than the 3d orbital. So right here, you can see the 4s is actually below 3d. We would fill in the 4s before the 3d. So there's potassium. Following the complete filling of a 4s orbital, then we go into the 3d. Yes, there we go. So once the 4s is full, then now we go into 3d. And again, we're going to put an electron in each orbital first, and then double them up. after that. All right, what we'll do is we'll stop the video there, and we will finish this in the third video.